Okay, so today, like I was saying a few minutes ago, I want to talk about reaction types. There are 4 different kinds. One of them is a single replacement, which is what we're going to talk about today, but there are 3 others. There's single replacement, double replacement, synthesis, and decomposition. Those are the 4. So that's where when the reaction type synthesis means you're bringing either molecules together or atoms together. So A plus B gives you AB. An example of that would be hydrogen and oxygen gas comes together to make water. A very simple reaction, but rockets use this all the time. Only they use liquid hydrogen and liquid oxygen, particularly during the 60s. Early Mercury NASA programs use this all the time. Now, if you ever see a rocket sitting on the ground ready to take off and you see all that stuff that looks like smoke billowing off of it, what it is, it's either liquid hydrogen or liquid oxygen. This is abbreviated LOX, LOX, HOX. And when those two come together, it forms this nice non-polluting product and a huge amount of energy. Huge amount. It's really something. Okay. And the opposite of synthesis would be decomposition. So that's when something is coming apart. So we could use the reverse water decomposing. This is how submarines get their oxygen when they're down. Submarines can stay underneath for months at a time. And what they do is they use this reaction here to make oxygen to breathe. A very common technique. Single replacement. There you have usually a metal plus a salt. Gives you another different metal based on the salt. And I'll show you what that means in a second here. Plus another salt. And I put those primes up there to indicate it's different. So this metal prime is different from metal. Salt is different than salt prime. Okay, that's what the prime means. It's used a lot in chemistry. You can have a single prime, double prime. So an example of that be so copper metal plus silver nitrate. You're going to see this as a demo today in lab. Yields one of 2 things. Either no reaction at all, I should say no visible reaction, or what's going to happen is the metal on the left is going to be converted into a salt. And then the salt here, the cation, the silver, is going to be created into a metal. Now, whether this reaction goes or not totally depends upon whether this wants to oxidize more than this wants to reduce. And you're going to have a chart. I'm going to show you the chart in a minute, and you go by the chart. Now, when you get to 1A, they don't use the chart. They use another, or is it 1B? Well, I forgot where they cover this, in 1A or 1B. I think it's actually 1B. Okay, and I'm going to talk in depth about this in a minute. Okay, the other reaction is called double replacement. And that's where you have two salts different salts. And when I say salt, what I mean by that is a cation and an anion together, like silver nitrate. Silver is the cation, nitrate is the anion. And that yields a different salt yet plus different salt. So basically, we're taking an aqueous solution. Aqueous means water. So we're taking a water solution of a salt and pouring it together with another water solution. That's the second salt. And what's going to happen is the anions and the cations are going to swap places. And that's where the new salts are created. And this is your lab next week. So as an example, we can take okay, silver nitrate, that's a salt. This is the cation, that's the anion. I'm going to put an AQ here, indicating it's dissolved in water, plus sodium chloride, another salt, dissolved in water. And what's going to happen is there's going to be a swap. And what's going to swap are either these two or these two. Doesn't matter which ones you swap. Either you swap the cations or swap the anions. It absolutely does not matter. So let's swap the cations. So that means the silver is going to go with the chloride. And the sodium is going to go with the nitrate. So these two are going to swap. So you have two new combinations. Now you started off with 2 and 2. Now we have 4 combinations because we mixed them together. Yeah. It says AQ for aqueous. That's a cursive AQ. Okay, so we have a beaker of this, a beaker of that. You dump them together. Now we have a possibility of the silver and the chloride getting together and the sodium and the nitrate getting together. Now, sometimes this anion and that cation may form a solid, or it may not. So you need a chart for that too. It's called a solubility table. That's for next week. And I have a special one for you guys that's much easier to use than the one in your lab. The problem is the one in your lab, it gives you rules to go by. The chart I have is very visual. As you take the cation and the anion, put them together on this chart, and if it's white, nothing happens. If it's black, a solid forms. Very visual, black or white. The rules, you got to figure out, I think there are four or five rules. And you got to figure out which class is this in versus this one. It's much more cryptic than mine. Mine is just super basic. Boom, yes or no. black or white. And I'll give you a copy of that for next week. Okay. So had we had this table, this would have ended up with as a solid, a white solid, and this nothing would happen. So we would put an AQ by this, assuming you had more room. But you don't know that unless you knew the rules or had my little handy dandy chart. Okay, so those are the four different types of reactions. Today, I'm going to focus on the single replacement, as you're going to do in lab. Your lab next week is on double replacement. And both these labs are kind of interesting. You're going to be putting stuff together and you're going to look at it. Is something going to happen? You'll observe something. Next week, colors will change. Solids form. It's pretty cool. Okay, so now the way your lab is set up is the lab would be like this. Let's combine copper metal and silver nitrate. Solution. Now, this copper with a 0 on top, that means it's not charged. That means it's a metal. A lot of instructors don't put zeros up there because this is an oxidation reduction reaction. Oxidation reduction. That means electrons are going to be transferred. And that means charges will form or charges will go away, depending on what you're starting with. So this is a combination of two half reactions. So the half reaction shows the electron part of the reaction. And the reason why it's called, my voice is fine. The reason why it's called a half reaction is because you need two of them together to make a full reaction. 1/2 plus 1/2 equals 1, right? Okay. Now, the reason why you have to put two of them all the time is you can't just have an electron wandering around. It's got to have a home. Okay? Got to have a home. So if we look at the copper part, which is the first half reaction, copper metal can lose 2 electrons. So this will be the half reaction for copper. When you lose electrons, that's called oxidation. So oxidation is the transfer of electrons. Now we have to balance that with another half reaction. So if you're giving off electrons, you have to receive electrons. So if we're giving off 2 electrons, how many electrons do we need to receive? 2. So that goes on the left. Now what's wrong with the reaction I just wrote? Huh? Yeah. This is a +1, that's a -2. Not good. So we have to have 2 of the silvers. So that's 2+. Because the silver can only receive 1 electron at a time. That's why you need 2 of them. Now, when we algebraically So we algebraically add up these two half reactions. We have to make sure that the electrons on the left and the right are equal. So when we add this up, we end up with the electrons canceling. We end up with, on the left, so you can never have oxidation and no reduction. Never, no exceptions. And this is abbreviated redox. Reduction, oxidation. Although they always say redox reaction, but they never say reduction oxidation. They always say oxidation reduction. No, anyways, abbreviated redox. So an oxidation reduction reaction is a reactions of electrons being transferred. So single replacement reactions are oxidation reduction reactions. Half reactions put together for full reaction. We're going to see double replacement reactions are not oxidation reduction at all. They're very different. Okay, so how do we know if this reaction is going to occur? So we have starting off, and notice there's silver nitrate. The nitrate is called a spectator ion. All it's there for is to balance out the charges. So what's missing is two nitrates here. And two nitrates there. So we have two silver nitrates giving us two nitrates here, two nitrates there. A nitrate is a -1 charge on your common ion chart. So that's why we need two of them here to balance out that +2. Now you see how all this is coming together? This charge stuff and everything. So when we finish this reaction, it's going to look like this. And then next week, we're going to be putting in AQs all over the place. Now you're going to see this reaction. It's going to be demoed for you up on the front podium there. Two reactions up there you'll be demoing. One is extremely slow. This one's fast. This one's really cool. You take copper wire, and you throw in some silver nitrate, and these silver crystals grow on the wire. It's really cool. Or the other reaction is actually very slow and very ugly looking. You form this sludge. But this reaction is pretty cool. Okay, so that's how to do these. The next question is whether this is going to work or not. So this basically means that copper is going to oxidize. And that means the silver is going to be reduced. But sometimes in the presence of two metals, one metal will not oxidize because the other one has already been oxidized. And it's more stable than the one you're trying to create. So that gobbledygook means basically that copper, since this reaction works, that means copper wants to be oxidized more than silver wants to stay oxidized. And that's on a chart. It's called an activity chart. And they give you that in your lab. right here. So the stuff at the top really wants to be oxidized. Super. Ones at the bottom don't want to be. So when you put two together, I'm sorry, what? Okay, so let's now go with what you just said. The first thing you do is you look at what you're starting with. They were starting with copper and silver. Now, if copper is the metal and it's above the other one, the reaction goes. If it's vice versa, there's no reaction. So if the copper was below the silver, there's no reaction. And these are going to be the charges on the ions you'll be using. And there are others, but these are the most common. So since copper, we're starting with copper metal now, is above the silver ion, that reaction is going to go. Okay, so all you need to do is the metal part. Remember, single replacement reactions involve a metal plus a salt. If the metal is higher on this chart than the salt metal, it's a go. Otherwise, nothing happens. Okay, and you're gonna have a lot of examples of this in your lab. What? There. Okay, so you're gonna be mixing various combinations, and you'll be looking at whether there's a reaction that occurred. Then you're going to go over to, you're going to see the combinations. You're going to go over to your activity chart and see where the two metals are. And there's one exception. It's right above the copper there. That's not a metal, hydrogen. So that's going to be part of one thing you need to look for is an acid. Is there an acid present? So for example, on the first one here, we're mixing copper metal with that stuff. That's an acid, sulfuric acid. Now, sulfuric acid gives off two hydrogens. So let's talk about what is an acid. Okay, an acid is a chemical compound that disassociates a hydrogen ion. Okay, so a strong acid kicks off all the H's that it can. Weak acids, it's partially disassociated. If it's not an acid, 0%. Now, if it has an acid, excuse me, back up. If it has an H in the compound, it could be an acid. It could be a strong one, a weak one, or not one at all. There are only 7 strong acids in the world. Sulfuric acid is one of them. So this is an example would be hydrochloric acid, sulfuric acid, nitric acid. And there are 4 more, but these are the most common ones that you run across in lab. Not so much nitric. In organic, you'll hit nitric acid, but sulfuric and hydrochloric acid, very common. Weak acids, there are millions of weak acids. All the organic acids are all weak. Acetic acid, vinegar, citric acid. These go on and on and on. The LSD, another weak acid. That's acetic acid. Now, if it's got an H, but it doesn't come off, it's not an acid. So if we have something like ethanol, drinking alcohol, this is what it looks like. Okay, it's got 6 hydrogens. That means it could be an acid, but none of them come off. So it's not an acid. Notice with acetic acid, there are 4 hydrogens there. That means we can have 4 leave, right? Only 1 leaves. That's the one attached to the carbon over here with the 2 hydrogens or 2 oxygens. Now, this all has to do with stability. Remember we talked about something going from unstable to stable? In the case of strong acids, that's a very stable reaction because it all goes. This is partial. So that means it creates something that's not as stable as a strong acid. This can't create anything at all that's stable, the least bit. This creates something called a carbon cation, horrendously unstable. That's why it doesn't happen. This produces something called acetate, which isn't too bad. That's why it happens a little bit, not a lot. And then this creates Cl- ions, sulfate ions, very, very stable. So it happens. Okay, so now when we're combining a metal and an acid, okay, so we have a metal plus a salt. The salt happens to be an acid. So let's look at the half reactions on these. So we have copper, loses 2 electrons. So the copper is being oxidized. And remember, it's a loss of electrons. So this is the oxidation part. And that means something must be reduced. Okay, so we have H plus here. That's from the sulfuric acid disassociating H pluses. And what's going to happen is notice it forms H2. comes from sulfuric acid. Sulfuric acid gives up those two H's, and they're +1 apiece. And if it was HCl, it'd be just 1. If it was nitric, it'd be just 1. That was a good question. Thank you. Okay, so now we have to figure out whether this reaction is going to go or not. Okay, so we go over to the activity chart here. We notice that the metal, copper metal, is below the hydrogen. So what's going to happen? Reaction or no reaction? No reaction. That's right. So nothing. Basically, you drop this into sulfuric acid and you end up with no visible reaction, or NVR. No visible reaction. Okay, so so it all depends on the relationship on the activity chart. If the metal is above it, it goes. If it's below it, nothing happens. So it's a real binary kind of deal. Does that make sense? Now you have an opportunity on your lab write-up to practice this a lot. And there's some, I have a lot of worksheets to practice too. I need to check to see if they're in your Canvas. Since I can't get on Canvas, I can't check. Can you guys get on Canvas? Okay, so that's what I wanted to cover today. I wanted to give you some background for today's lab. Tomorrow, I'm going to talk about something called moles and molar mass and Avogadro's number. And you need that information to finish your hydrate lab. And then next Friday, I'm going to talk about double replacement reactions. So you can do the lab on double replacement reactions. Now, there's some tricky parts on double replacement reactions. We're going to take that in 2 days. 2 days. Okay. All right. That's what I wanted to cover today. So if you haven't got your tests, they're up here by initials of the last name. And for those of you who have lab today, I'll see you in lab. Yeah. Huh? Next week for the double replacement reactions. And then tomorrow we're going to talk about moles.
So I noticed on here, right? So when my numbers were different. Is that just because the orbital was more stable when you did it? Do you know what I mean?
Well, this is very unstable because of that there.
Uh-huh.
And you wrote it correctly.
Oh, okay.
They said, then correct if not valid.
Okay, cool. Thank
You
you.
did a nice job of that, by the way.
Today I was checking and I saw like that pen is late and I panicked and I posted the lab with the half one we did and I even wrote a note. So am I late or I know we have to cover, and even I wrote in the notes we have to cover the mass and moles. So how do I?
Which lab?
Then
Oh, let me turn off the
Yeah, yeah.
recording. Does this make sense today?